Excellent. Thank you, Jermaine. So I'm Evan. I'm a student of Magdalena's, actually based in the University of Queensland. I'm just here visiting. I'm here to talk about the localization problem in the Unruh-DeWitt model. This is based on a paper I published earlier this year, along with Magdalena. You can find it in Physical Review D. So to start off with, we'll start very broad. So in relativistic quantum physics, it has its origins in the 1900s. It started with Einstein developing special relativity and quantum theory. In the 1920s, we developed relativistic quantum field theory, but we still have a bunch of open questions in the context of relativistic quantum mechanics, namely, how do we define a particle in quantum theory? Can we provide a consistent single particle description of relativistic quantum mechanics? And what does the transition from relativistic quantum field theory to non-relativistic quantum mechanics tell us? This last question is particularly helpful in looking at quantum gravity and aspects there. To explore some of these questions, we look at the Unruh-DeWitt detector model. This was originally proposed by Unruh and then simplified to a monopole type system by DeWitt. The basic idea is that we have some two-level system, like an atom or what we call a detector, which we couple to a quantized scalar field. Usually it's a scalar field. The interaction Hamiltonian takes the following form, which features this monopole operator, or also called the polarization operator for those coming from atom-light interactions in atom optics. The basic idea there is that we can change the energy level of our detector in its coupling to the field. The field can be decomposed into a superposition of some mode functions. Here we take the plane wave modes. We are simply working with a Minkowski spacetime. The Unruh-DeWitt detector model has quite a few different applications. It was originally studied in the context of curved spacetimes for quantum field theory, but it has also been applied in the context of relativistic quantum information, particularly looking at entanglement harvesting and such, mainly entanglement type applications. Recently, it has also been used to develop an idealized model of the atom-light interaction. Where have I gone? Okay. We want to extend the model a bit to feature a quantized center of mass, because usually we treat the detector as some point-like model. That can lead to problems that we might want to resolve, that there are a few ways of developing this model a bit further. The first such extension was proposed by Unruh and Wald, where we take a detector localized to some blocks, and we have some discrete energy levels for a detector, which we can then obtain the following monopole operator as a function of the wave function for the ground and excited state energy levels. Another way, or alternative way, of introducing a quantized center of mass was developed by Strisselberger and Kempf. Here, this is more along the lines of an idealization of the atom-light interaction, and so we do not have any such potential confining our detector. So our detector can delocalize or spread out. We introduce a kinetic term into the detector's free Hamiltonian, where again we're assuming some non-relativistic detector, like in the previous Unruh and Wald model. An equivalent model was treated by Wilkins in the context of the atom-light interaction, where the electromagnetic field was employed rather than some scalar field. And so this stuff has been looked at quite recently and gotten quite a bit of interest. But we want to go a bit beyond these two models, because both of them assume this non-relativistic detector. So what we really would like to do is to treat the center of mass relativistically. There are two different ways of doing this. One is through a second-quantised model in the framework of relativistic quantum field theory. The other is to try and model our detector in a first-quantized way within the framework of relativistic quantum mechanics. We're going to consider both of these models, but let's start with the second quantized one. So in this case here, actually it goes back to Unruh's original paper. Unruh proposed two models for the detector, one being this first quantized box detector model, and the other was this second quantized fully relativistic model. In this case here, the basic idea is we're replacing the ground and excited state levels of our monopole operator with ground and excited state fields, which allow us to model the change in the mass of a detector. The interaction Hamiltonian takes the exact same form, where we have again our monopole operator appearing, with the small caveat being that the coupling constant now is distinct from the first quantized coupling constant. They're dimensionally different. I'll speak about that in a bit more detail later. Now, this model was simplified in a quite recent paper by Giacomini and Kempf, where they restricted this model to the one particle sector. So they're restricting the Fock space of the detector. When one does that, then the position and internal degrees of freedom are coupled, and you obtain these position states that appear in the interaction term. Now, this looks very similar to the non-relativistic model that we previously looked at, except that the position states here aren't quite defined as you might expect from non-relativistic quantum mechanics. They feature the Lorentz invariant integration measure appearing here, and as a result, one does not have a Fourier transform of the position states in terms of the momentum eigenstates. So that's actually quite interesting, and it leads actually to a bit of an interesting question here. Before that, there are a few caveats to clarify. So one might actually ask, hang on a second, why do we have two detectors here, psi g and psi e? Well, we only really have one detector, and there's different ways of factorizing the Hilbert space here. In this case, we factorize the Hilbert space to have a ground and excited field, but we can also separate out this internal degrees of freedom, and we only have one center of mass for this detector field. This is really just giving us an effective description of the detector in terms of this composite scalar field. Another caveat is that this detector is not running localized. This is what I sort of mentioned briefly. So in looking at the model developed by Mr. Zellberger and Kempf, no potential is postulated, and so the detector will spread out or delocalize over time. Typically, one wants the detector to remain confined to a finite region. This is why Unruh proposed a box detector model originally. And more recent work has also been developed by Eduardo Martinez and Rick Pierce. In principle, one can synthesize these two different notions of localization by confining potential and localization in terms of a center of mass, although we don't develop that in this talk here. Okay, so I've outlined the second quantized way of treating a detector's localization. We could also approach the localization from the opposite direction, where we take a first quantized model and we attempt to make that more relativistic. The most obvious way of doing that is we choose a frame in which our detector is boosted, and we simply quantize the Hamiltonian, in this case here putting a hat on the P. We also have to put a hat on the M, because our detector is some atom or some two-level system, and we have to describe the change in the energy or mass that results from the state in which it's occupied. A good motivation for this might also be neutrinos, which exist in mass superpositions, and where we would have this sort of possible projective operator on the internal states there. Okay, so the interaction Hamiltonian we expect for our first quantized model will take the same form as it was in the non-relativistic case we expect, where we have some internal degrees of freedom and we have these position degrees of freedom for the center of mass. But we have to be a bit careful about how we're defining a few things. So in particular, what time parameter is our Hamiltonian generating time translations with respect to? So I've been working in the Schrödinger picture just to avoid any explicit time dependence for the moment. But the simple way is that given that we have an inertial detector, and conventionally when one wishes to speak of the Unruh-DeWitt model, one evolves with respect to the proper time, we can simply take a frame, at least in this inertial system, to coincide with the coordinate time. Our proper time coincides with the coordinate time. That's just by given time reparameterization. More carefully, we have to actually define what these position states are in this sort of first quantized picture. So we could employ the same localization as we found in the quantum field theoretic model, but it's quite natural to take the Fourier transforms to just be, to take the position states to be Fourier transforms of the momentum eigenstate, in which case it would entirely agree with what we have from non-relativistic quantum mechanics. And the very last point is that, as I mentioned before, the coupling constants between the two different models disagree. So we have to actually find some way of relating the two models in terms of this coupling. What we do is that, or what we expect, is that when the detectors are at rest, the two models should coincide. And so that gives us a constraint on how to compare the two couplings and how to make them dimensionally equivalent, given by this proportional term in terms of the masses of the detector. Okay, so a brief summary is that we have a first quantized model. It's given by this linear combination of the this term here appearing in terms of linear combination of the ground and excited energy levels for our first quantized localization, which is just a Fourier transform. But for the second quantized model, it's exactly the same thing, except that we now have, of course, a different coupling constant, and we have this Lorentz invariant integration measure appearing in our localization. Okay, so we proceed as we do, as per usual, in the Unruh-DeWitt model, which is that we want to look at some particular observables of the system. Here, a small caveat is that we're treating this more as an idealization of the atom-light interaction. And so usually one treats a detector which goes from the ground to the excited state, and we interpret that as a detection of a particle. Here we're treating our detector more as an atom where we take it to be in some excited state initially, and we want to look at the spontaneous emission of our detector to some ground state energy level, which leads to an emission of some field quanta. We work in the interaction picture, so all of the evolution will now be done with respect to the free Hamiltonians. And of course, we look at, we assume weak coupling, and we look at things to first order in perturbation theory. Okay, so of course, we just go through the usual methods. We find the transition amplitudes and probability. And what we really care about here, and usually what's reported, is the transition rate. If you go through all of the calculations, you'll obtain a transition rate given of this form, which is a functional of our detector wave function, convolved with this template function, it's called. This template function has units of energy in our definition, and it effectively encodes all of the dynamics from the Hamiltonian for the given system that we want to consider. Okay, so looking at the different first quantized and second quantized template functions, we find actually something that's very interesting, resulting from the two different localization schemes we've prescribed. In the first quantized model, we have a result that's proportional to the relativistic dispersion relation, while in the second quantized model, it's proportional to the reciprocal of this dispersion relation. And just to illustrate that a bit more explicitly, we have this quite different physics going on here, which is very dramatic for large momenta. This can also be compared to the classical case where we're not keeping track of any of center of mass, and so the template function just coincides with the energy gap. To get a few more results, we can also consider a non-relativistic detector and a semi-relativistic detector. This would be equivalent to the previous models I gave at the very start of the talk, where we have just a p squared on 2m for our kinetic term. In this case, we have quite a different behavior for low momenta, even in the regime where we might have interesting effects. The semi-relativistic case is something that I've coined, but basically, when we have two different energy levels for a detector, we have this mass defect corresponding to the splitting of the ground and excited energy levels. If you want to include that in the description of the dynamics, then you get something called this semi-relativistic regime, in contrast to just treating the mass as some C number, which isn't quantized. Okay, and this is, of course, for very small energy gaps. You can also consider it for larger energy gaps. Here again, we have the same behavior for our relativistic models. There's some disagreement here between the classical cases. This just comes from which mass we have chosen to normalize with respect to. So everything is with respect to the ground state mass. We could have also normalized everything with respect to the excited mass, which would likely, we would likely find that these different models would coincide if that were done. Okay. To get a few more explicit results, what I want to do is I want to assume our detector has some Gaussian profile. This can generally be assumed because we can always, for some arbitrary distribution, take a saddle point approximation of our full distribution and obtain some kind of Gaussian approximation. We can actually get analytic results if we assume that our detector is at rest. And in that case, we obtain this Gaussian product with a modified Bessel function of the second kind for the first quantized model. For the second quantized case, we get this hyperconfluent geometric function out. And we can then also plot and see what the different models look like. In this case here, we have the width of our Gaussian to be larger than the Compton wavelength. And we find that the relativistic first and second quantized models agree. They coincide. That's actually perfectly expected because if you remember from the template function I showed before, both of the two models coincide when you're at rest. Quite interestingly though, if we localize below the Compton wavelength, then one does actually get disagreement. Of course, this is a bit suspicious because we can't really localize below the Compton wavelength, unfortunately. When you start doing that, so the usual argument goes, you have enough energy to create particle-antiparticle pairs. And this would destroy any kind of localization that one might want to achieve. So ideally, one would look at this for general momenta or higher momenta. Unfortunately, I've so far been unable to achieve results for that case. One has a very highly oscillatory integral that doesn't even allow for approximation methods like the stationary phase approximation. So I can't obtain explicit results here. But just by looking at the template functions, one knows that when we convolve our probability density function with one of these template functions, we will get very different results. But of course, all of this is heading to a really important question, which is what would one observe if this experiment were performed? Would we expect to see the results of the first quantized model or from the second quantized model? Which of these localizations is actually the correct one? In fact, maybe there's actually something wrong we've done here. Can we even define our relativistic position operator as equivalent to this non-relativistic position operator? Which of these position operators is the correct one? And going back even further, how does one define a relativistic center of mass? So this is maybe getting a bit away from the quantum mechanical side of things, and it is sort of focusing on a particle-based interpretation. You can develop this in a more field-theoretic framework, but historically this was developed with particles in mind. If we have some many-particle system, then the way that we define it in non-relativistic center of mass, forget relativity for a second, is it's just the weighted average of the position vectors. And this is some unique definition. Everything gets a lot more complicated when we bring relativity into the picture. Because in fact, there are different ways one could define, or reasonably define, a relativistic center of mass. And this was first investigated by Price. I put an asterisk there on first because no one ever, the person who's claimed to be first is never actually first. And this is true here. There's people a bit before Price that looked at this, but Price gave out 6 different definitions for a relativistic center of mass. All of these sort of are sort of quite sensible. The first two are basically choosing some frame, a Galilean frame or a rest frame, where you, like in the Newtonian definition, weight the position vectors by the rest masses. In definition B, you also then can obtain results by just transforming according to the Lorentz group. Now, there's a few more definitions, of course, that they listed out, but the ones that we actually care about are actually just definitions D and E. So here we define our position vector in the rest frame weighted by the dynamical mass energies, and we transform according to the Lorentz group. And in that case, we have a Lorentz invariant position operator. We can alternatively define our position operator in coordinates where we have a vanishing Poisson bracket. And in that case, we actually have a result that agrees with the intuition of A and B in that we have things appropriately defined in the rest frame. Okay, so following from this kind of idea, it's going a bit now away from this viewpoint of a many-particle system, though. We want to define how a relativistic position operator should be thought of in terms of quantum mechanics. And Newton and Wigner approached this question by requiring any properly defined position operator satisfy a set of invariance conditions. All these conditions are actually really quite intuitive. So if we have some localized system, then these localized states, taking a superposition of them, should also remain localized. It should be invariant with respect to spatial rotations and reflections. The states should be orthogonal with respect to translated states, which is kind of getting at the idea that we should have a delta function if we take the inner product of these states. And lastly, the generators of the Lorentz group should be applicable to these localized states. If we do all of this, we in fact find that this is equivalent to Price's definition. In fact, sorry, I should say definition E, because there are 6 of them. This is from the fact that we have a vanishing of the commutator, which is a result, I think, mainly of condition C. In the classical limit, this would correspond to the vanishing of the Poisson brackets. And moreover, this also coincides with the non-relativistic position operator. So this is exactly the quote-unquote first quantized position operator that we introduced. And it is, or in other words, the first quantized system, we imposed a Newton-Wigner localization. However, there's different ways of defining a position operator in relativistic quantum mechanics, as we've just seen from the center of mass discussion. So Phillips approaches this from a quite different, the exact same approach in terms of defining variance relations, but wants to impose different constraints to define what a position operator is. So in this case, we again have the first 2 conditions as we had before, but we add a different constraint, which is that the localized states have to be invariant with respect to Lorentz boosts. And this condition is actually not compatible with the other conditions that we impose from Newton and Wigner. But to make sure that our position states are uniquely defined, we also have to have a few more properties. So of course, our localized states should be normalizable within some finite region, and our localized states should be irreducible. This definition is exactly equivalent to Price's definition D in terms of this Lorentz invariant localization. And just a small aside, moving more towards a second quantized interpretation or field theoretic interpretation, these Phillips states are equivalent to the action of a field operator on the vacuum. Okay, so we have 2 different localizations. I don't have the time to go into all the details here, but one immediate question that one can ask is, how are these 2 localizations related? And the answer to that is they're related in a very interesting way in that you can map between the 2 and the associated operator representations via something called the Foldy-Voltaisen transformation. And there's been a lot of discussion of this transformation and also of localization more broadly, which says that there's a very close relation between what these 2 definitions of a center of mass sort of describe. But moving away, I guess, from that transformation, just to focus on localization itself, how should we be interpreting these two different things? And the answer is it's a bit unclear. We expect, I guess, intuitively that the more fundamental second quantized model should be correct, but its position operator is not Hermitian. Now, this is maybe looking at things from a more particle-based ontology, which is that starting from what Phillips was thinking about, we have some well-defined particle. We want to define a position for it in a Lorentz invariant way. The operator there is actually non-Hermitian. It's a bit more natural when you look at it in a field theoretic perspective, because, well, it's just going to correspond to the field operator. Meanwhile, the operators in the Newton-Wigner representation agree with what we expect, particularly in the classical and non-relativistic limits. But there's no Lorentz invariance for the localization, and in fact, we have some non-locality issues. So is this Newton-Wigner representation the result of coarse graining, or does it have a more fundamental status? There's some open questions here that we have to ask. But just to quickly summarize, the localization problem in the Unruh-DeWitt model is what we sort of have come across, also for the atom-light interaction, if one treats this as an idealization. There's some surprising disagreement between the first and second quantized models. And in principle, these are experimentally distinguishable if one takes a detector boosted with respect to the lab frame. It leads to the very important and interesting open question, which is, what is a particle? Well, this has already been answered, really. The conventional answer is just a particle is what a particle detector detects. But then we can ask a bit more, what is a particle detector? Well, a particle detector is some localized system from which we can perform local operations on a quantum field. But now we again push it back a bit more and so, okay, well, what is meant by a localized system? For a relativistic particle detector, how should we define its localization? And this is starting to get into answers that I don't have at the moment, but which, of course, we'll hopefully be looking at. Okay, thank you.